Hey there, geometry students. Well, last time we talked about how parallelograms have certain properties, 5 properties to be exact, and today we're going to do the opposite. We're going to, give you some properties, and you're going to prove that things are parallelograms. So in order to do that, we're going to use the converse. So here are kind of listed the 5 theorems, so to speak. The parallelogram opposite side parallel theorem. The parallelogram opposite side congruent theorem. I guess I forgot the congruent symbol there. Okay, but what we're really more concerned with today is the converse of these, because our mission is to prove that a quadrilateral is a parallelogram. So, for instance, like this one right here, the converse would be if opposite sides are congruent, then the shape is a parallelogram. And this is basically true for all of them. If the diagonals bisect, then the shape is a parallelogram. If the opposite sides are parallel, then the shape is a parallelogram. And when we are proving that a quadrilateral is a parallelogram, it is sufficient to just show one of these properties is true. If one of these properties is true, well, then all the other properties have got to be true as well. Okay? And so that's our mission. All of these, the following questions are ways of proving or showing that a quadrilateral is a parallelogram. So this type is actually just IC2 in disguise. For what value of x is this quadrilateral a parallelogram? Well, it's almost identical to the questions that said this is a parallelogram. Find the value for x. We're going to do the exact same thing. If these are congruent, and I can make these two congruent, well, then the diagonals bisect. And that would fulfill the parallelogram diagonal bisect theorem converse. And so what we'll do is we'll just go ahead and say x minus 32 is equal to 4x. And so we'll subtract 8x, we get negative 32 equals negative 4x. So x equals 8. The only difference here is I might go ahead and just ask you to say something like, therefore, if x equals 8, then this is a parallelogram. All right, we mentioned in the last lesson that it's going to be real common for you to see a lot of coordinate proof type stuff here. This isn't necessarily a coordinate proof, but it is on a coordinate grid, so in that sense, it's close. Remember, we only have to prove one of those things is true. Some of them might be more convenient than others. Okay, remember the 3 major formulas that you're going to use whenever you're dealing with coordinate proof stuff. You've got the distance formula. And so if I wanted to prove that the opposite sides were congruent, I could calculate the distance of each opposite side and show that they were the same. That might take a while, but we could do it. The other formulas that we worked with, the slope formulas. If I wanted to show that the opposite sides were parallel, I could find the slope of each one, show that the slopes were the same, and that would be enough. I probably could do something with the angles, although that might take me a bit of work. I don't know if I would want to do that. The midpoint formula is another one that I could use. If I wanted to find the midpoint of both diagonals and show that those were the same coordinate, well, that would prove the diagonals bisected, and that would work too. Me personally, I'm going to use the slope formula. I think that's going to be the easiest. You can use whatever you would like. And so I'll label this quadrilateral ABCD, and I'll just try to stay organized here. We'll kind of label it slope so that the reader knows we are finding the slopes. Let's compare AB and DC. So the slope of AB, well, let's see, it looks like 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5. 5 over 5 would be 1. let's hope CD is exactly the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, 5 over 5 is 1. So those opposite sides are parallel, but don't forget we've got to do it for both. So let's compare AD and BC now. AD, down 1 to the right 2. Got a slope of -1/2. And then BC, well, BC, that looks like it's also going to be -1/2. And as with all kind of proof-related type things, this isn't a real proof, it's specific to this example, but we can say that, therefore, this is a parallelogram by the parallelogram opposite sides parallel theorem converse, the Post-Pitic. All right, moving on, an actual proof, a T-chart proof, something that we are painfully familiar with. Now, don't get all excited. If I tell you, given the opposite sides are congruent, you can't just say opposite sides congruent theorem. You can use anything but that to prove that. Now, we don't have to worry about that here because we don't have any full properties. We've got 2 half properties. We've got that these are congruent, and if these were congruent, that would be nice. We've got that these are parallel, but we'd need to know that these are parallel as well. Well, here we go. Step 1, BC is parallel to AD, and BC is equal to AD. That's been given. Step number 2. Remember how I told you, at least in class, that typically your best strategy is to turn these quadrilaterals into 2 triangles, because then, generally speaking, we can prove that these triangles are congruent, and then use CP/CTC to show that other things are congruent, and that is helpful. So we're going to create AC, and that's just an auxiliary line. And, well, now that we've got that, what can we say? I'm pretty sure that we could just say that AC is congruent to AC. That would be by the reflexive property. So now we've got 2 sides. We need another side, but that's really not going to happen. Or we could do an angle. We've got to be careful because we don't want ASS. We've talked about that many times throughout the year. If anything, we're going to want SAS. So let's go ahead and label this guy angle 1 and this guy angle 2. If I do that, I would have, well, let's see, I could say that angle 1 was congruent to angle 2. Why? Well, because I've got alternate interior angles. I know that these 2 are parallel, cut by a transversal, and these 1 and 2 are alternate interior angles. So those have to be congruent. So the alternate interior angle theorem. And now I could simply say that, well, triangle ABC is congruent to triangle CDA. And that would be by the side angle side. You can see it here, side angle side, side angle side. Well, we're not done. We would have been done if that were chapter 4, but this is chapter 8. So we need to prove that this is a parallelogram. Well, I can use CP/CTC to say that AB is congruent to CD. That would be, again, by CP/CTC. And now I've got 2 sets of opposite sides congruent. And so I'm going to say that ABCD is a parallelogram by the parallelogram opposite sides congruent theorem converse. All right, well, that takes us through lesson 3. Next time, we'll be talking about some very special parallelograms.